Dear audience, this is a fracture mechanics approach to hydrogen-assisted microdamage in cracked samples of high-strength eutectoid paralytic steel, resembling Michelangelo stone sculpture texture. I am Jesús Toribio and work at the University of Salamanca, the oldest in Spain and one of the 4 oldest in Europe, with this very beautiful logo representing the bishop, the castle, and the lion, and the priests. Summary: 1. Introduction, 2. Hydrogen embodiment tests, 3. Macroscopic crack model, 4. Model results, 5. Conclusions. Let's go to the introduction. The Theory Topography Surface, TTS, is a microfracture mode appearing in fracture tests on cracked and notched samples when tested under hydrogen charging. This is the appearance of tearing due to hydrogen. It's a kind of hydrogen-assisted microdamage. We have observed experimental results showing phenomenological relations between the size of the TTS region and different variables, e.g., for cracked samples, the electrochemical potential, and the maximum stress intensity factor during fatigue pre-cracking. The aims of the work to model the TTS region as a macroscopic crack that extends the original fatigue pre-crack and involves linear elastic fracture mechanics principles. To analyze the critical stress intensity factor, Kh, that is reached when the change from TTS to cleavage takes place. To demonstrate that the value Kh depends on the value on the fatigue pre-cracking regime, the SIF Kh depends on this level of fatigue pre-cracking, and to elucidate the influence of the TTS geometry on this parameter Kh, the critical SIF, the critical stress intensity factor under hydrogen-assisted cracking conditions. Let's go to the second part, hydrogen embodiment test. We have performed hydrogen embodiment tests on eutectoid paralytic steels, 0.78% of carbon, mechanical properties of the steel, Young's modulus 195 gigapascals, yield strength 725 megapascals, UTS, ultimate tensile strength 1300 megapascals, fracture toughness kit 0 asterisk 53 megapascals per square meter, and the critical stress intensity factor, K1C star 65 megapascal per square meter. The first one, the fracture toughness, is measured with cylindrical pre-cracked specimen trying to achieve the plane strain conditions, whereas the critical stress intensity factor is measured with prismatic pre-cracked specimen. This is the fracture surface of the round bars. We have a notch, starter notch, after a fatigue pre-crack, H0, and the TTS fractographic mode, subcritical cracking under hydrogen-assisted cracking conditions, hydrogen embodiment conditions. Then, after the fatigue pre-crack H0, we have XTTS. This is a fracture mechanics approach in which the hydrogen-assisted microdamage represents an extra crack prolonging the original fatigue pre-crack, a mechanical fatigue pre-crack, and an environmental crack, posterior crack produced by hydrogen-assisted cracking in the form of tearing topography surface. Final fracture by mechanical reasons by cleavage. Then AH, the total crack depth, crack length is AH, equal to H0 plus XTTS. Then we have an addition of the mechanical fatigue pre-crack H0 and the prolonging tearing topography surface depth. Let's go to the third part, macroscopic crack model. The crack model is as follows. KH is equal to the dimensionless SIF. KH is the critical stress intensity factor, SIF, in hydrogen environment. YH is the dimensionless SIF, dimensionless stress intensity factor of the fatigue pre-crack plus TTS extension, AH. is the total crack. Sigma H is remote stress applied on the cylinder. And AH is the total cracks, the original fatigue pre-cracks, A fat plus XTTS. We have the sigma H equal to 4 times the load FH at the critical situation divided by the area of the cross-sectional area of the cylinder. D sample diameter, 12 millimeters, FH, the fracture load in hydrogen. As a reference value, we have the K0 equal to Y0, the dimensionless sieve, sigma 0, and the square root of P and A0. K0 is the material fracture toughness in air, Y0 the dimensionless sieve, dimensionless stress intensity factor, fatigue pre-crack in air without TTS extension, and sigma 0 remote stress applied on the cylinder. Is obtained by the load, fracture load in air, F0, 4 times and divided by the diameter of the cylinder. Then we have the crack model with these two values, critical sieve KH in hydrogen embrittlement conditions, hydrogen assisted cracking, and K0, the same value in air. We divide the two values of the critical stress intensity factor in hydrogen and in air, and we have the ratio from the YH to the Y0, and also the ratio of the stress in hydrogen and in air, and the square root of the ratio of HH and H0. The total fatigue pre-crack plus the TTS extension divided by the original fatigue pre-crack without the TTS extension. We obtain this equation representing the ratio of the two values of the stress intensity factor. The crack characterization is as follows: a semi-elliptical crack, central part, the crack center A and the crack surface B, and the two parameters defining the crack geometry and crack aspect ratio, the crack depth A minor A, and the other axis of the ellipse B. We have this distance H and the position X of any point at the crack line. We use the Shin and Chi expression of the stress intensity factor. Then with this expression by Shin and Chi, we obtain these equations. AH to BH is the crack aspect ratio after hydrogen embrittlement, A0 to B0, the crack aspect ratio to fatigue pre-crack, A0 to D is 0.3, and A0 B0 is 0.78. The coefficients M are from a table by Shin and Kai in 2004, and AH is the total crack, is the original fatigue pre-crack, plus the depth of the TTS region. This is the TTS zone approach, and the model results as follows. We represent the KH divided by K0, KH divided by K0, the ratio from the critical sieve in hydrogen to the critical sieve in air, as a function of the same ratio for Kmax, the maximum sieve, maximum stress intensity factor Kmax during fatigue pre-cracking, divided by the fracture toughness in air K0, critical sieve in air. We represent this increasing trend for different values of the aspect ratio of the hydrogen assisted cracking flow, the hydrogen assisted crack, the fatigue pre-crack plus the TTS extension. Variation of Kmax versus KH is quasi-linear or linear, KH as a function of Kmax, with a higher increment of KH when the TTS zone aspect ratio, AH to BH, decreases. Again, we have a decreasing trend with the crack aspect ratio of the hydrogen crack, hydrogen-assisted crack. The influence of the variation of AH to BH on KH is higher in those TTS regions resembling a semicircular shape, and the ratio here we represent the KH to K0 versus the crack aspect ratio of the hydrogen-assisted crack for different values of the maximum fatigue pre-cracking load, fatigue pre-cracking intensity Kmax for different values. The influence of AH to BH on KH decreases when Kmax becomes smaller. Let's go to the conclusions. When a high fatigue pre-cracking load is applied, the value of the critical SIF in a hydrogen environment is higher, so steels that are subjected to heavier pre-cracking exhibit a higher resistance to hydrogen damage. Variation of fatigue pre-cracking load Kmax versus critical SIF on hydrogen KH is linear, with a higher increment of SIF in hydrogen when the TTS zone aspect ratio decreases. The maximum variation is reached when the TTS zone aspect ratio is null. It is a straight TTS crack front. TTS zone with the highest aspect ratio near to unity have lowest value of SIF in hydrogen, so it can be thought that hydrogen effect is higher in TTS region with a high aspect ratio. The variation of the influence of the TTS zone aspect ratio on the critical SIF in a hydrogenated environment is higher in those TTS zone geometries resembling a semicircular shape. After these scientific conclusions, an epilogue, resembling Michelangelo stone sculpture texture, which is the subtitle of this article. We have observed that this tearing topography surface TTS resembles the surface of the Michelangelo Pietà di Firenze sculpture, which is placed in the Museo della Opera del Duomo in Firenze, Florence in Italy. Then this Michelangelo Pietà di Firenze represents Michelangelo stone sculpture texture, MSST, resembling the tearing topography surface or the aspect of hydrogen-assisted microdamage. Another work by Michelangelo, the unfinished Pietà Rondanini, also resembles the tearing topography surface, TTS, the zone associated with hydrogen-assisted microdamage in perlite microstructures. This Michelangelo's Pietà Rondanini allows us a definition of Michelangelo stone sculpture texture, MSST, resembling the aspect of the hydrogen-assisted microdamage at the micro level. Hydrogen-assisted microdamage in the form of tearing topography surface in perlite. And that's all. Thank you very much for your kind attention, and I am showing the beautiful logo of my university, the University of Salamanca. That's all.